All right, physics, here we go. Magnetism and magnetic fields. We will cover those two things as well as the relationship between electricity and magnetism, aka electromagnetism. So we've already seen that mass distorts space, and we modeled that with what we called a gravitational field. We also saw that electric charge can distort the space, and we modeled that with an electric field. Well, magnets must be doing something similar. They must be distorting the space in some way because little pieces of metal near a magnet seem to feel the presence of that magnet. So there must be something akin to a magnetic field as well. The way that magnets behave has some similarities to the way that we saw electric charge behave. The opposite so-called poles of a magnet attract one another, whereas like poles will repel one another. But the question is, where does magnetism come from? Is it like gravity, just a fundamental property of anything with mass, or electricity, a fundamental property of anything with charge? And the answer is sort of complicated. We can look to a certain extent at magnetism as a fundamental property, and we can look at particular atoms and how they may or may not have it. We can go up one level higher and look at how atoms join together to potentially have magnetism, and then go up one level higher still to see if just solid chunks of stuff will have magnetism. A really good video on this is by Minute Physics, and it'll be better than what I'm about to do, so you should check that out if you like. Minute Physics, search that and you'll find his really good video on where magnetism come from. But here's my version. To a certain extent, the electron is a tiny, tiny magnet, or the fundamental particles have fundamental magneticness. However, that doesn't mean that every atom is going to be magnetic, because here's a helium, for example. Its two electrons have their little tiny magnets pointing in opposite directions, and so it cancels itself out, and helium has no intrinsic magnetism. So if you look at the periodic table, we see that the sort of elements that do exhibit intrinsic magnetism occur around the same place on the periodic table, because it really is about their electron shell configurations that will leave, that basically there needs to be just the right arrangement so that they don't cancel themselves out. And the periodic table doesn't really have many great natural, the universe doesn't produce many great natural magnetic elements. There's really only a handful: magnesium, iron, cobalt, and some weird ones over there which I haven't heard of. But just because you have an element that's magnetic, that doesn't mean that when you get a whole bunch of those elements together, you're going to have a magnet. So when atoms join together in a pure substance, they form a crystal. Now, if they bond in such a way that neighboring atoms, like this little atom here has his magneticness pointing up, and the atom that he's bonded to has his magneticness pointing down, the net effect of that little pure crystal is you don't have any magnetism. So what you need is for those little, you basically need a crystal structure that doesn't do that. So you need to have an element that's magnetic, and then you need to have it bond together in a crystal structure that doesn't cancel itself out. But even then, you need to satisfy one more criteria to actually pick up a piece of stuff and have a magnet. The domains need to be aligned. So when you say domains, I mean, if you pick up a piece of iron, it's really made up of thousands of little tiny crystals of iron. It's not like one solid chunk of diamond, which is, pure, one big molecule. A regular piece of iron, just thousands of little crystals joined together. And those little tiny crystals represent little tiny magnets. And if they are not aligned, then you still won't have a magnet. And so, what to say? So here's, oopsie, PowerPoint crashed. Really hope I can delete this gosh damn section out. If not, sorry kiddos, you're having this awkward interlude. Alright, so here's a piece of iron, and the little tiny crystals' magneticness are all pointed in different directions. This is your standard school magnet that has been dropped 100 times. That's what it looks like. But when iron is sitting on planet Earth, and planet Earth's magnetic field passes through it over time, the little pieces of iron can sort of align themselves, and you get naturally occurring magnets that you pull out of the ground. The good news is you can put something that is magnetic in the presence of an external magnetic field, and you can force those domains to become aligned so you can recharge your magnet. You can also induce magnetism in the similar way to that we induce charge. So you can bring a magnet up to certain metals and they will be attracted. So we do represent the space around a magnet with a field, and by convention, just like we said, electric fields point away from a positive and towards a negative, magnetic fields go away from a north pole and towards a south pole. Now, when we defined electric fields, we were like, oh, what happens when you put a positive charge here? Which way will it go? And that's how we define the electric field. Well, for a magnet, we say, oh, what happens if I put like a compass needle just here? Which way will it point? Because a compass needle really just is a little magnet. And so whatever way a compass points, well, that's the way we say that a magnetic field points. So compasses always align themselves pointing towards the South Pole and away from the North Pole. And you're probably thinking, did I just make a mistake? No, I didn't. So, yeah, magnetic fields point away from a north and towards a south. The compass is pointing toward the south magnetic pole. Nice, cool. Yeah, so this gets confusing when we think about planet Earth, because our compasses point towards the North Pole. Now, that's kind of what north means, right? That part of our planet up the top there. So what's going on here is that the geographic North Pole is a south magnetic pole. Yeah, sorry about that. That's just the way that it goes. So our magnets do point towards the south magnetic pole. It just happens to be the geographic North Pole. However, it gets even more weirder in that the actual North Pole, like if you followed your compass north until it stopped pointing north anymore, so you sort of just spun freely because you're at the pole. If you got to that point, you wouldn't actually be at the same point that the Earth rotates about. So there's the North Pole about which we rotate, and then there's the North Magnetic pole, which is a south magnetic pole, and those 2 points don't align. So the axis and the North Pole are not always the same. In fact, they shift all the time. If any of you have ever done like navigation, you know that you have to look up, you have to adjust your compass if you want to do any sort of accurate navigation. So your compass always points north, and you spin your compass around till it touches N, and then you know you're headed north, except that your compass is actually pointing towards the north magnetic pole, which is a south magnetic pole. And so you have to adjust for where the actual true north is. And it changes every year. So that you have to, if you do any navigation, you have to like look up your chart, like, oh, okay, if I'm in Brisbane over here, whenever this was taken, I think this is from 2005, my compass, when it points to the north, won't actually be pointing towards the correct North Pole. I have to adjust it by 10 degrees. And that's how they adjust for that. Yay. Additionally, you probably never do this, but if you put your compass sideways, like this one, it will sort of incline itself up or down in some way, shape, or form, because the magnetic field around the planet Earth doesn't just go horizontally across the planet. Depending on where you are on the planet, it has a certain incline, and the closer you get towards the poles, the more downward that field points, and we call that the angle of inclination. That also changes every year, just so you know. If you're pretty much along the equator, that green line there, the magnetic field is more or less horizontal, like we expect it to be. But as you get, like, look down at Australia, so if you get a compass, you could expect it to incline itself at about 60 degrees. So the magnetic field passing through wherever you are right now watching this, it is coming up out of the floor, since we're closer to the South Pole. Wait, no, we're closer to the North Magnetic Pole, so it's going down into the ground. Ugh. Here's a fun question. What happens if you cut your magnet in half? You would get, would you isolate your magnetic poles and have monopoles? No, you would not. There's no such thing as a magnetic monopole in the way that we could do this trick with electric charge, like we could get positive and negative charge and separate them. We can't do it with magnets. It doesn't seem to work. Why? Because magnetic fields point from north to south, like that. And when you chop it right there, you still kind of have the remaining arrow that you had before. You still have your old field. Chop that in half, and you still have the field that's going in that direction. So it's like chopping an arrow in half. It doesn't stop it from pointing in a certain direction. Just like we had uniform electric fields, yeah, you can get uniform magnetic fields between parallel magnets. But here's the kind of most important part. What is the link between electricity and magnetism? The story behind this is pretty darn cool. This guy was doing magic tricks with stuff he didn't really understand, making big electric currents. So he had this wire, closes the switch, lots of current flows through, and he had his compass nearby, and he noticed that it deflected whenever he had current. He's like, whoa. So the electric current is messing with the magnetism. That's a pretty darn big discovery. Yeah, tech issues. Skip forward on your video until you see the PowerPoint appear again. Talk to the person next to you. Just kidding. see if this works. Should be a sweet animated GIF coming through on my video. Nope, scratch that. Oh well. What Hans Christian Ørsted discovered is that what magnetism is really, or where it comes from, is electric charge that's moving. When electric charges move, they create magnetism. Check this out. There's a big whopping big current and a whole bunch of compasses, all pointing in one direction, and or pointing north probably. Turn the current on, bam! They all align themselves in this sort of circular pattern. Right, so yeah, the magnetic field around a current carrying wire wraps itself around the wire in a circular way. We have this rule, the direction matters, by the way, so does it go clockwise or anti-clockwise? We have this weird rule where if you just imagine yourself going and grabbing the wire and you point your thumb in the direction that conventional current is carrying, your fingers will wrap around that wire in the way that the magnetic field goes, in that circular way. So see how his fingers go in the same direction as the field. It's called the right hand rule. So the magnetic field around a current carrying wire, since current is moving charges, we can draw like this. The left one is sort of self-evident, sort of three-dimensional kind of field you can imagine. We sometimes want to draw this in a two-dimensional way, and so for fields that are coming out of the page, we draw dots, and for fields going into the page, we draw crosses. And just like for electric fields, the closer these things are together, the stronger the field is. So the field is quite strong up close to the wire, and then gradually gets weaker as you move away, as you would expect. There's a cool way to remember these dots and crosses, is to think of a bow and arrow. So if someone shot an arrow at you, what would you see? If that arrow flies towards you, you see a dot that's about to kill you. If you're the one shooting the arrow, you're going to see the little feathers flying away from you. Yeah, it's a cool way to remember. So we can also draw current coming into and out of the page, and we'll draw a circle with a dot, current flowing out of the page, circle with a cross, current flowing into the page. There is a formula for how strong is that magnetic field. Pretty simple formula. It just depends on the strength of the current and the distance you are from the wire. The unit of magnetic field, which we call magnetic flux density, is the Tesla. Yes. Something cool, if you get a wire and you wrap it in a circle, and let's see if this works. Oh yeah, cool. Inside that loop, all of the field lines point the same way, and so when you loop a wire, you get a really sort of condensed magnetic field in the middle. So we loop wires to get really, really strong magnets, basically electromagnets. And if you ever want a quick way to figure out which way the magnetic field goes through the loop, you can imagine yourself holding the loop. As long as your thumb is pointing in that direction of that current, your fingers will pass through the loop in the way that the magnetic field does. When you loop something a lot, we call it a solenoid or an electromagnet, and you get really strong fields that are almost parallel inside. There's another little rule you can use for figuring out the direction of the magnetic field in a solenoid. This time, use your fingers and wrap them, and since when your fingers are sort of curled, they look kind of like a coil. And so as long as your fingers are curled in the direction that current's going, this time your thumb points in the direction of the magnetic field. So that field would be flying out towards the left. So those are the three sort of fields I've talked about: current carrying wire, single loop, and a solenoid. Oh, and bang, that's a real life one. Turn on the battery and those little tiny bits of iron get manipulated. That was fun. There's a formula from the textbook, and this is what you guys need to do. Get busy. Don't forget to leave a comment, hit like and subscribe. No, just kidding. Yeah, maybe you could comment questions you want me to go through. Happy quarantine.